Thank you. Yeah, it's truly a pleasure to be here. It was about 25 years ago. I was at a meeting here right before I was a postdoc here at NCAR on a similar topic, and so it's been kind of exciting, I guess, to see how much this area has grown and the kind of influx of new ideas. So it's really fascinating. My background is kind of different. I actually have graduate training in both atmospheric science and statistics, but then kind of ended up on the stat side of things at the end of the day. And so this is one of these talks where probably somebody in the audience knows something much more about what I'm going to talk about than I do. But maybe that'll help, in some sense. So this is work with Patrick McDermott, who was a PhD student who finished up and is now at Jupiter, who's here in the audience. So really, it's kind of my naive statistician's perspective on some of this stuff in deep learning. And really, the situation that I want to deal with, I've worked my whole career in building spatio-temporal dynamic models that kind of respected science in some sense. And as fun as that is, and as interesting as that is, it kind of breaks down in certain situations. One, it takes a long time to build some of those models. And so they're not so portable. And the other thing is that sometimes we don't have enough data to really do that the right way. So if you don't have a lot of data, but you still have a complex process, what are you to do? And that's one of the things I want to talk about. And then, can we use some simple or parsimonious models where we don't have to estimate a lot of stuff and do it efficiently? And then kind of at the back of this to me is can we do this in a way to quantify the uncertainty, which I think is important. So modeling interactions in spatial-temporal processes usually requires nonlinear models to do it right for real-world stuff, depending on the scales of variability. And we know that deep models, both statistic deep models and machine learning deep models, can do this, but they can be pretty challenging to implement once you get into the weeds. And so what I want to talk about today is sort of, can we get that same kind of predictive power, but in a more parsimonious framework? And so I'm going to resurrect these notions of echo state networks, which have kind of are sort of passé now, I think, in the deep learning, machine learning world, but I still think they have some value. And so really what we're going to do here is show that we're going to do a regression at the end of the day, and we're going to transform, it's sort of like a basis function regression. And our inputs are going to be transformed in a dynamical way, but we're going to do this in I guess, a formal statistical model. So pretty simple stuff. It just sort of seems weird at first. And so this is just to illustrate that there is this complex interaction between things like the ocean and the atmosphere, of course. We've heard that so much here. And then this is soil moisture. And there's all sorts of scales of variability here. And again, I'm sort of preaching to the choir. You all know that. If you look at these things, I'm gonna do something I probably shouldn't do because I shouldn't. The whole point of me using my own computer was to not use preview. Yeah. Sorry, a nice awkward silence never hurt anyone. All right, so the animations didn't work in preview. Anyway, so the point here is that things are not static, right? They're dynamic. You see this interesting stuff like the waves that you see in the Pacific, in the tropical Pacific, associated with Kelvin waves propagating through there. You see similar things related to different scales of variability in soil moisture in the U.S. And so obviously there's connections between these things. And if we're going to model this, we need to sort of incorporate those connections. And so in particular, I want to talk about long lead forecasting. And that is a climate problem because it's on scales beyond the weather forecasting scale. And you say, how can you really do this? We've seen examples already in this conference about the uncertainty associated with chaotic dynamic systems, like the REN system, for example. And so if we know we have that and we can't do weather forecasts beyond, say, 10 to 14 days, why can we do this? Well, it's come up already. It's because the ocean operates on a much slower time scale, right? And the ocean is connected to the atmosphere and to other things. And we've heard about teleconnections, and so what happens is, for example, in El Nino, is that the warm pool shifts, and the tropical convection clusters shift, which leads to wave trains that teleconnect to the northern and southern hemisphere, and adjusts where the jet streams go, and so it changes the weather impacts. And so in particular, say we're interested in soil moisture, which I am in this particular talk, and I want to predict that, then it depends on the state of the system in terms of the ocean. And then that's going to impact things like precipitation over this region, which would then impact soil moisture. And soil moisture would be important, obviously, in this central part of the U.S. because that's the primary corn-growing part of the country. So sea surface temperature is the key to make all of this work. So if we're going to build models to do long lead forecasting, you could take two approaches. You could do a deterministic approach or a statistical approach. And this is one of those situations that came up earlier today where statistical models actually do about as well, if not better, than deterministic models. And the reasons for that, I'm probably not the best person to address that, but the reasons have come up too, right? The things that make what's going on here is interactions across the ocean, boundary to the atmosphere on many different scales, and then how that influences precipitation, which then how that influences how moisture is distributed in the ground, and et cetera. All of those interaction processes are not known very well. You know, we know a lot about each of those things individually, but when we look at how they're coupled together, we really don't know that much. And so this is a place where we can take advantage of that through statistical models. And I think this is an example of some of the parameterization ideas that came out yesterday as well. So typically there's two approaches that you could do. You could take sea surface temperature, and you could then forecast that forward in time, which there's a lot of models to do that. We can do that pretty well, actually. And then you could just couple that contemporaneously to, say, soil moisture. So it's kind of a two-step process. So there's nothing wrong with that, except do you really need that extra, you need that sort of first step there, or can we go directly, which I would call a more regressive approach, where you would say, I'm just going to take the soil moisture at the current time and see how it related to sea surface temperature back, say, 6 months or 7 months or something. And this is much more of a regression approach, right? There's not really there are dynamics going on there, but it's not like I have a dynamical model for sea surface temperature here. And that becomes important in my talk here. I'm going to focus on this approach today. We certainly do it both ways, but I'm going to do it here, and then I'm going to show the benefits of sort of thinking about some of the deep structures that we might have in between these two levels. So if you read the book that I wrote with Noel Cressy, or at least if you have it on your shelf and use it for something, if you open it up, nobody actually reads it, right? If you open it up, you'll see this somewhere, that we sort of believe that in statistics that you definitely have to separate the measurement process or the observation process from the state process. And that's not an uncommon view outside of statistics either, right? In engineering, that's been around for a long time. So you model the observations on this latent process, and you could call it a true process or whatever, or a latent process. And then that latent process is going to have some fixed effects. You know, I'm still a statistician, so I still think that way. You could call that a bias term or a trend term, whatever your favorite terminology is. And then there's this dependent random process. And that dependent random process, the dependent part of that's super important, right? I mean, there's spatial, there's temporal, there's spatial-temporal, multivariate interactions going on. It can get kind of crazy. And so in statistics, we spend a lot of time on this. And in spatial statistics, where I grew up, you know, the models that you might have heard of, like Kriging models and Markov random field models and point process models, this is where they live. They live in that space. And so that's what we'll focus on here, typically. So the main challenge, as I mentioned, in long lead forecasting is really this notion of there's all these different time and space scales that are interacting. And these models that we typically do, like the Kriging models and things, are not very good at dealing with that, right? When you build a model based on the second order properties of the system, you've already thought about things being marginalized out, so it's hard to get that in. You've got to start thinking about it a little bit differently. One way to do that is what we would term a deep model. And everybody has their own definition of that. I have a definition that just says I basically have an output that's linked with a bunch of telescoping models to some sort of an input. Okay, and you could think about that differently, but I think that's kind of what most of them are, right? One way or the other. And in statistics, we've been doing deep models for a long, long time. We just didn't call them that. And this is an example of one. Developed here at NCAR by Mark Berliner back at the beginning of the geostatistics project back in the early 90s. And the idea was really simple. I take this joint distribution of everything that I care about, the data, the process, and the parameters and whatnot. And then I break it up conditionally into a series of linked conditional models. And so they have a data model that gives data conditioned on the process and parameters, and then I model the process separately, conditioned on the parameters, et cetera. And these are all, the product of all those things will give you this joint distribution of all this stuff. And what a simple idea, right? And then the cool thing is, then Bayes' theorem tells us how to actually do the inference, right? We just say, okay, I can flip that around and say the process and the things, parameters I want to learn about given the data is a product of all three of these things, at least proportional to that product. So all good, all well and good. I mean, the devil's in the details here, right? What this paradigm did is it allowed people to sort of break their problem up into different conditional levels. And this is exactly what happens, in my perspective, when somebody starts working with a deep model, right? Regardless of whether it's a stat model or a machine learning model. And so the key, this often gets lost on statisticians, but the key to the Berliner paradigm was actually that you want to avoid modeling second order things. Covariances are hard, right? And the more you have to put stuff in covariances, the more it slows down everything. And we don't know that much about how things behave in the second order typically. And so you put as much structure as you possibly can in the conditional mean. And if you think about most of the deep models in machine learning, at least the ones that I'm familiar with, and I'm no expert, there's not much covariance modeling going on there, right? You're sort of taking one part, a hidden layer, and it's getting messed around with and pushed it into another one. Very much a first order operation in that sense, right? And that's because we were marginalizing complexity through that process. The whole deep linked model paradigm is allowing us to marginalize complexity up through the hierarchy, right? And that's why both hierarchical Bayes models and deep learning models work, right? Because we've split these things up into these smaller components. Now there's some similarities and there's some differences. The BHM models are very much top-down models. You know, the data's at the top, and then we start building stuff that go beyond at lower levels. You can put inputs into different levels, but usually it's up close to the top where the data live. And here's just a really quick example I'll just breeze through. So you have a data model, say Z is something that I care about. Maybe it's soil moisture, and then the true latent process is Y. And then I'm accounting for the observation error here somehow and my representation error in this data model. And then I might say, okay, I'm gonna model this latent process Y and some transformation of that in terms of things that I could write down, like a mean process, maybe seasonality in the mu. And then there's gonna be this dimension reduction part typically, some basis functions, maybe some spatial basis functions and some coefficients. And this is the part that's gonna have all the cool dynamics in it. Okay, and then I have some residual stuff that's left over I need to deal with. So I could put another model on this mean part and put some extra inputs in there if I want. And then again, the workhorse here is this dynamical process, this alpha. And so this is where I've spent most of my work, is trying to come up with efficient statistical models to do that actually make sense from a physical point of view. And probably about the closest thing I've gotten to do that is what's called a quadratic nonlinear model, where you have basically quadratic interactions. And there are a lot of challenges with that, and we weren't the first to do it, but we were sort of the first to put it in this kind of a framework. And so you have a residual process, but the key to making this whole thing work after the dynamical model is this regularization notion, right? That we have to start shrinking parameters, so many parameters and so many state variables in these things that the curse of dimensionality kills us. So we have to start regularizing. And those of you who do machine learning, this is what you do, right? This is why we do lasso, this is why we do elastic net, this is why we do all sorts of things that regularize. And then finally, we have to close this system out. You know, if you're a turbulence person, you think about this as a closure problem. I think about it as just specifying the hyperparameter distributions. Okay, and then we would go through this hierarchical model, and they're all linked together. We can do formal uncertainty quantification. All the uncertainty propagates up and down, but the challenge and the thing that makes it really not so easy is this notion of hierarchical Bayes MCMC implementations. So if you can do this, then it's going to work really well, usually. Okay. So here's the other example, and now I'm out of my league. So this is a deep sort of neural model, and you can see it's kind of similar, right? The difference, I would say, this is more of a bottom-up model from my perspective. But you have your inputs, it's going to go to a hidden layer. You're going to mess around with those hidden layers and do some sort of reduction, usually. And then you keep doing this, right, until eventually you have an output layer that connects to your output. Now, again, this is a pretty simple version of this. But what's the similar part about this is that there are things like pre-training that are sometimes done that is a lot like putting a prior on what we would have done in the Bayesian context. Regularization is almost always included in this kind of optimization strategy. The thing that's a little bit different is that we aren't always doing uncertainty quantification here. We aren't really necessarily accounting for the uncertainty in our inputs and necessarily accounting for the prediction uncertainties. Depends on the problem, it depends on the method. So here's a list of things that similarities. There are multiple connected levels. Dimension reduction has to happen. They don't typically include second order dependence. You can handle multiple inputs and predictors at different output types, not necessarily at the same time. I'll come back to that later on. A lot of things to estimate, a lot of parameters, hidden states to worry about. They require a lot of data, both BHMs and these sort of deep models require a lot of data. Some sort of prior information. You got to get you got to regularize into the sample space somewhere, or into the objective space somewhere. And then you're going to have to use some sort of computational efficiency in your algorithmic approach here. So the question that I have, and that Patrick and I had when we started doing this was, okay, so what if we didn't want to do either one of these? Because it just was too slow, and we wanted to do it on our laptop, and we wanted to do it in a situation where we didn't have tons of data. And so we thought, well, okay, what would we do to get dynamics in? Well, obviously, you know better than I do. You would go to some sort of recurrent neural network framework, and those have been around a long time. And it's great because you can, if you want, you can build memory into those, but you're certainly getting this notion of time dependence in, and we could do that in a spatial-temporal context, and people do that. And so these have been around, but they still have the same kind of challenges, right? Even though it's not a deep model, it still has the same challenges of lots of parameters. Estimation is a challenge here through the vanishing gradient problem, et cetera. This is what the very simplest version of an RNN would look like, and Rose showed this yesterday as well. You know, the nice thing is you do get this sort of transform Markovian kind of structure happening, which is very much like what we would like to think about from a physical perspective, typically. You have inputs that influence this. If you think about this, there's no stochastic term, right? So this is really just a transformation of our inputs. It's sort of a kind of a telescoping transformation. And then I take that, and then I do some sort of regression at the end of the day, or some sort of a classification type model there. But I just want you to think about this for a second. This is just some transformation of X, right? That's all it is. And we'll see if we can use that. So there are more state-of-the-art RNNs, but they're only going to be more difficult than this, not easier typically. And so what about the parsimonious versions of these things? And so I hadn't heard of an echo state network because I didn't know anything about any of this stuff. And then Patrick sort of dug this up, and this whole notion of reservoir computing became pretty interesting to me. And you'll see why, I think, in a second. So it looks very much like, and those of you who are really experts in this, just ignore what I say. So it looks very much like an RNN, right? There's a couple extra parameters here that help control sort of the guess keeping these things from blowing up in some sense. But the key difference between this and what I showed on this page was that we do not estimate these parameters W and U. They're just drawn at random from some distribution that ensures that they're small and that it's sparse, right? So as a statistician, this is like, how could this possibly work, right? How could this possibly work? I'm not estimating any parameters here. And but I also am like, I'm psyched by that because I don't want to, that's the challenge, right? So this is good. I have to estimate the output parameters, but I know how to do that. That's just regression or discrimination or something. Not a problem. So this is cool. So what we did is like, well, how can we do that in the space-time context? So we started playing with it. We wanted to add some uncertainty quantification. We wanted to add some error on the data portion of the model. We allowed there to be a quadratic output of the hidden states because quadratic effects are important in a lot of space-time models. And then the only thing that we really did that kind of made this work well for the kind of dynamical space-time problems we cared about was we had to use embeddings. So all that means is we take lagged versions of our inputs. And in Rose's talk yesterday, she indicated how important it is to get these higher order interactions going on for nonlinear processes. And we totally agree with that. But one way to kind of do that cheaply and more efficiently, rather than put it on the hidden states H here, is to let there be embeddings in the inputs. And of course, we're not the first to have done that. And this is just Tocken's theorem, right? We can recreate the state process by enough lags of some component of that state process. And it turns out that this helped a lot. These are the distributions that we draw from, just basically a direct at 0, so we have a lot of zeros here and then a bunch of small values. And then we have to choose just a very few parameters through some sort of validation procedure. The only other thing that we did is we added a parametric bootstrap to this so we could do uncertainty quantification. I mean, why just sample those matrices one time, right? That's crazy. I mean, engineers do that, and they make a much wider network, but we thought, well, we have a bunch of smaller networks, and we do this parametric bootstrap, and then we can also get uncertainty quantification. So we get the power of ensembling, and we get the power of uncertainty quantification. And we also did a fully Bayesian version of this, which I'll mention in a second, but I won't show you that. So the first thing we applied this to was just a long lead forecast of sea surface temperature. And this is a problem that has been around forever, and it's hard to beat like a linear inverse model, right? There's still really good models, and if you can't beat a linear inverse model, then you should just kind of go home. But you can beat them in certain situations, typically with a nonlinear model, particularly the warm phase of the El Nino. And so this is actually, those of you who tried to forecast the 2015-16 one, it was a pretty challenging El Nino to forecast. And this is sort of a hindcast, but it did not use these data in the training. And it did a nice job, did a pretty good job. And this is sort of a series of out-of-sample predictions that the model did. And so, we were pretty pleased by this because it takes like 15 seconds to run this model, right? A fully Bayesian version of this with quadratic interactions takes about 10 times, 100 times longer than that, right? So pretty sweet. So I first presented this in 2017 at the Joint Statistics meetings, and before that, I did this or asked Patrick to run the model on, from the closest thing we could do with the data we had at the time. So we took December data and we forecast for June, and these were the results we got, and I was like, oh, I'm not going to present this because obviously our method doesn't really work because all the suite of ensembles that the Climate Prediction Center put out, this is what was going on, this was our prediction. And so I didn't present it. I just said, yeah, you could do this in real time, and I didn't do it. And then it turned out this verified, this is the verification that this model actually did better than all the other models at that time. Now, that's probably just random, but at least we did have uncertainty quantification to suggest that it was a reasonable prediction. But it was it at least kind of opened my eyes to the fact that maybe this thing had some legs behind it. So it worked well on that problem, but why? I mean, it's weird, right? We're not estimating parameters, really. So it's got dynamics in it, but we're not really the dynamics aren't really being learned, right? They're just being sort of handed down. So there are some things that matter, right? There's nonlinearity being captured because we've got this embedded inputs. These small, sparse, random parameter, these weights, definitely prevent overfitting, and they kind of add to regularization. Because we have a fairly small number of hidden states, and we have a bunch of ensembles, we're really getting each one of those are independent. We're getting an ensemble of weak learners, or committee of weak learners. You've heard that terminology before. So that's kind of nice. And it's practical. It's super, super useful. And it takes, like I said, 15 seconds to run. Now, it's not deep, though, right? It's not a deep model. So if I were going to model something that had multiple time scales and spatial scale, there are multiple spatial scales in the El Nino prediction, but something like the soil moisture long lead prediction, it's going to require more than that, right? Because I've got the ocean and the atmosphere interacting on multiple time scales. So we thought, well, maybe we need a deeper model. Maybe we need a deep version of this. And so clearly there are deep models in RNN type models, right? There's the GRUNN RNNs and the CNN RNNs. I mean, it's like there's a lot of C's and R's floating around there. There's deep ESNs too, right? If you even look back into the mid-2000s, there were deep ESNs. They didn't really do uncertainty quantification so much, and they really weren't spatial temporal. So we thought, well, what could we do? And what could we do quickly? Can we implement quickly? And so we went back to this notion of what's really going on here in a deep model, in an ESN model, or any of these kind of models, is a transformation of your input, right? They're really basis functions, right? We're creating basis functions. So we're going to use a deep echo state network model as a stochastic transformation, because that's really what it's doing of our predictors. And then we're going to take an ensemble of those, and we're going to let those be potential predictors in a spatial temporal regression, which we'll regularize. So we did this, again, in a parametric bootstrap way, and then as a fully Bayesian way. I'm going to present the Bayesian way because it shows you a very, very simple hierarchical Bayesian model in a way that's still using deep stuff as well. So this is what the model looks like. The data stage, again, so we have some sort of transfer, the data, and then we have to, some latent process that we care about, and we'll talk more specifically about what that is. And then we're going to model this latent process, in this case, in terms of some beta coefficients, just like a regression. And then a bunch of different transformations of our inputs, okay? So there's N, N of RES of these things floating around, and then some air. So pretty simple. We'll put some regularization priors. I'll go into detail on that. But the key is, what's this stuff? Right? What's this transformation of my input? And so this is where it comes from. So this is just a deep echo state network. So if I start at the bottom here, here's my embedded inputs. It goes through an echo state model. Again, I didn't have to estimate any of these things. They're just drawn. Right? It's not supervised at this point. That then goes through a reduction stage. You can pick your favorite reduction here. I'll show you what we use in a second. And then that goes into the next stage and blah, blah, blah until you get to the top. Okay? So why are we doing this? Well, the same reason we do deep models all the way around, right? We're trying to learn things slowly at different scales in time and space. Or in this case, we're not learning them. I just said it was unsupervised. So in this case, we're not learning them, but we're creating the possibility of these things, right? That's what all I need. All I need is just some new inputs that might be better predictors than what I had before. And so that's what this is going to give me. And again, this is the same as before. The parameters in the echo state deep model are just drawn. There's no estimation, there's learning there, it's just boom, sample them. Okay, there's a few parameters that we do have to choose, and we can do that, as I'll talk about in a second. So this is the full model. And you don't have to be a Bayesian here. You could do lasso on this. You could pick your favorite frequentist method with shrinkage. It has to have shrinkage, but it wouldn't matter. So in this case, it's just a regression version, so it's Gaussian. There's a dimension reduction done here through a spatial basis function. And then we model the residual structure and the measurement error here in this covariance. This is all specified and very low parameters, a number of parameters. And then this is just our regression. We split it up because at the very top level we use everything. We use this without it being reduced, and then the other levels we use the reduced versions of them. And then this function here just kind of puts it on the same scale back. So there's way too many parameters here. I've got zillions of betas and zillions of potential covariates here, and so I have to shrink them down. And so you could pick your favorite shrinkage method. We really like stochastic search variable selection in the Bayesian context, and so that's what we use. But basically, there's a probability that these things are zero, a high probability, and if they're not, then they're small, and that's just how this works. So we can learn that. It's important to note that this is a two-step procedure, and that these transformations of these stochastic transformations of our inputs happen offline, right? And that can be super highly parallelizable if you want it to be. Right? We don't have to do that while we're fitting the model. The hyperparameters here, again, there's a bunch that are fixed because it's just not very sensitive to them. The hidden layers, number of hidden layers, we all are fixed here, except for the first one because, again, we use dimension reduction anyway, and it doesn't make too much difference. And then the ones that are left, we'll use a genetic algorithm. And this is the only slow part of the process, and even that's not super slow to train these things. Okay. Dimension reduction in that step of the deep model, again, you could do what you like. We use PCA here. You could also try Laplacian eigenmaps. We've done that. Or your favorite nonlinear reduction. But more importantly, you could do things like extreme learning machines, which are just kind of like echo state networks for dimension reduction. Or you could do your favorite convolution pooling procedure. Because these are spatial things, right? They're spatial fields in some sense. It just didn't matter a whole lot in this particular problem for us. And when PCA works, use it, right? It's super simple. And it almost always works to some extent. This may not be the best. Okay, so when we evaluate things here, we'll look at mean square prediction error. But there's two other things that are super important for us. One is we're interested in the uncertainty here a lot. So we need a measure of the distribution quality, not just the prediction itself. And so we'll use continuous rank probability score because that's sort of become the default standard, at least in my world, to look at distributional forecast. And then we'll also look at some skill scores because that's what climate scientists like to see. So that way you can compare a model to a reference. Okay. So to try this out, you saw yesterday in Rose's talk about potentially doing this stuff on a Lorenz system. The simple 3-variable Lorenz system isn't really representative of what we're doing because we have a space-time system. So people have, since Lorenz did this in 96, there's a spatial version of the Lorenz model, right? And that looks kind of like this. This one's a little bit more complicated, but basically it's quadratic interactions. It still represents sort of atmospheric type processes and has chaotic dynamics. There's also a multi-resolution version of this that people have been using in the applied math world for a few years. And so this is where you have multiscale Lorenz interactions going on. So this Y process gets interacted with the X's. Here's how Y interacts with X, and then X interacts with Y. And then we just added a data stage onto this because we wanted to think about this. So the underlying process is this coupled Lorenz system, but the output is whatever you might see. And in our case, we're going to look at something that looks kind of like what soil moisture profiles might look like, or precipitation profiles might look like. So this is what, it's kind of a star plot, but this is to show you that these are the spatial locations corresponding to, say, for example, the fine scale part of this coupled Lorenz system. And then there's the larger scale part of the process is given by these blue dots. So each of these reds would influence that particular blue dot. And then this is the output transformation. So we actually have more variables than this, but this is just an illustration that it's a continuous spatial domain. It's one dimension in space and in a torus framework. So this is what it looks like, a simulation. So this is just 3 of the 18 locations. This is the output, and this is the hidden layer that corresponds to the large-scale Lorentz system. And again, this is just ones associated with those locations. And then even though there's actually 20 red ones associated with each of these blue ones, we're just showing 4 here. So these are the small-scale ones that feed into this. So it's a coupled system of sort of not super strongly nonlinear, but nonlinear system. And you can control that level of nonlinearity if you like. So in this case, what we're going to use to demonstrate this method, this Bayesian ESN model, we're not going to use anything from the x and y's, the hidden part of the Lorentz system. We're only going to use the output and lag values of the output. And we're going to forecast forward three time periods. Again, that's sort of arbitrary because you can make the time periods as small as you want here. And then we're going to use 3 embeddings here. This was chosen through a genetic algorithm. And we have like 510 periods. So we looked at models from 2 to 8 layers. And this is the best one. It turned out to be a 7-layer model. And so remember what it's doing. It took its 7 layers of this ESN transformation to be able to figure out that latent coupled Lorentz system, spatio-temporal Lorentz system. And it did a pretty good job, actually. So the red here is the posterior mean prediction. The prediction intervals, I'm not sure you can see real well here, but they're given by these gray things. And then the truth is given by the black curve. So not too bad. And those are all out-of-sample predictions, of course, at 3 steps ahead. So that was enough to suggest that this might work. So in the real-world case, what we did is, again, we're interested in this soil moisture problem. Oops. And let's see if this will actually work. And so the interesting thing about the soil moisture and sea surface temperature, again, is note that they do operate on different time scales. There's no doubt about it. That it takes a while for what happens in the soil moisture profiles over the continental U.S. To change, right? They just don't change quite as rapidly, but they do change, and you can see clusters of spatially correlated regions, and how those regions might change through time. Whereas the ocean, even though it's operating on a much slower time scale, when you look at it, the stuff that's actually showing up is all the small time scale stuff. Right? You don't see the long time scale stuff near as clearly in that. So the procedure has to be able to sort of sort that through. Right? It has to be able to find the scales, the right scales in time and space to make this work. So just let me talk about this before I talk about the results here. So we did this, soil moisture, nobody really has gridded soil moisture over this kind of region. But there are models that have assimilated it, and the NOAA produces one that we use. So it's a product. So our output here is a data product that goes back, we used to 1948, 2011 as training period. And we basically did a dimension reduction on that with the first 15 EOFs, or spatial temporal components. And then the residual part of that was included in the data model error term. And then our forecast inputs are based on the first 5 EOFs of sea surface temperature in the Pacific. And again, then there are going to be embedded versions of that as well. So those lag versions of that will be in the input space. And so we're only interested in predicting in May, even though the model was trained on all the months. And why May? Because May is sort of one of the most crucial times for corn production in this part of the world, because that's when planting happens, right, for the most part. Okay, so how did it work? So this is just two years, and you can see pretty different periods of amount of soil moisture, and just between 1 year, right? And that's not unusual to see that. There's not a great deal of autocorrelation necessarily across years in soil moisture. There's some, and depends, some locations more so than others. But let's look at May 2014, for example. And then this is our prediction, our lags, our 6-month out of sample prediction. And yeah, is it a perfect forecast? No. I mean, this is a hard forecast problem. It's also hard because linear models don't do a terrible job here. In certain parts of this domain, a linear model is actually going to be better. And the challenge is you don't know where that's going to be. So you don't really know which parts in which year the linear model would do better than the nonlinear model. And then fortunately, we do have some uncertainty quantification that we can apply to this. This year, things actually look pretty good as well for the general pattern. There are places where we're off a little bit. If you look at South Dakota, for example, sort of messed that one up. But again, any long lead forecast problem is pretty challenging. And so, is this better than the current products? From our evaluations, it tends to be, and I'll show you a map here. Well, I'll show it and then I'll come back. This is a scale relative to climatology, so anything that's sort of above this 0 color is good, and below is bad. And so, yeah, there's certain parts of this domain where this model is actually not performing really well. That didn't surprise us. If we did an ensemble of different types of forecast models here, we could probably have done that better. But for the most part, it does a pretty good job. And if you do the skill score compared to the linear type models that people typically use, it does better in most places than that as well. Okay. So this is kind of interesting. So this is what the most, I guess, frequently chosen input hidden unit predictors were. And the point about these is that at that point, they're time series, right? And so you can see that there's all sorts of interesting time and multi-scale kinds of behavior going on there. I have absolutely no idea what these things mean, and I don't think anybody does, because that's sort of what, if you think about it, they've gone through so many different layers of transformation that their interpretation is really difficult. But perhaps there's some learning that could be done on that, and that's a topic we could talk about here in a second. Just to show you how well this all does compared to some other models, just the basic ESN model, different 2- and 3-layer models, linear models, climatological models. In terms of the prediction, the 2-layer Bayesian model did the best. The 3-layer model actually showed the best in terms of uncertainty quantification and the best sort of skill predictions. So again, it matters what criterion you use to compare these things. But overall, it looks like it did a pretty good job. So just to recap, this is really, it is just a regularized spatial-temporal regression, but the inputs here are stochastically and dynamically transformed. It's interesting, those of you who, if you know me, you know I always work with dynamic models, but this is not a dynamical model, right? It's just a regression model. But it's dynamic in the sense that the way that the transformations that happened to my inputs were very dynamical, right, through this RNN type structure. And so that's kind of different, right? So you don't think about that when people do generalized additive models, which is, I have a comment here that this is kind of what this is. You have a basis function transformation of your x's, and then you regress that, right? But who does this, right? Who does it stochastically and then in this really complex nonlinear dynamical context? I mean, you don't have to, but that's one way to do it, clearly. The multiple copies, of multiple levels of transformation allow the different time scales, which is what it turns out to be important here. And the multiple copies, that's why we have so many of these things that we do, we replicate that ESM process, that D process a lot, because we need that for reproducibility, or for some people call that stability. If we don't do that, then if I only did that once or twice, then I might get a good prediction, but the out-of-sample predictions would be terrible. Right? We need to have this replicated a lot of times, but it's fast. It's, like I said, it's parallelizable, super fast, super efficient. Very easy to do this in these kind of models. You can easily compute this on a laptop in minutes, as opposed to a fully Bayesian hierarchical model, which would take probably all night to run on a bigger computer. So, in conclusion, there are lots of processes in the environment and ecological world where I work that are best thought of as nonlinear, at least on many scales. Parametric models I love them. I mean, I grew up on them. I still do them. I love to work with scientists on those kind of models because that's how we learn. But those are not the best kind of models for off-the-shelf prediction, right? Because you've got to put a lot of time and effort into developing really good parametric models in this space. So the deep models are going to be helpful, as I mentioned before, because that's how you build complexity up slowly, and you marginalize that complexity up, because otherwise it's going to be hard to write down a likelihood. There's no chance of writing down a likelihood that makes sense, that can deal with this kind of dependency. Deep machine learning models are super powerful, and the more I see people do them, the more impressed I am. But I also am impressed by the computational resources they have and the amount of data that they have. And we don't always have that, right? So these echo state networks, even though they're sort of dead in the water, I think, in the machine learning community, I don't think they should be. I think they still have a place, and particularly if you kind of use them to assist modeling as opposed to being the be-all, end-all of your model. The standard deep models in this framework don't really accommodate uncertainty quantification, but you can see we could do that through parametric bootstrap or putting them in a Bayesian context. I should mention that we have fully Bayesian versions of all this stuff, and they all work better in terms of uncertainty quantification, almost never better in terms of prediction, and they're much slower. And Patrick could attest because he spent tons of time developing it, so they're a pain in the ass. Okay. So these transformations that we do here, though, are super simple. I mean, fast. I mean, you could program it up yourself in R or Python in, 15 minutes. It's that simple. You don't have to rely on somebody's code that you don't understand. You can just do it yourself, or you could. I'm sure you could use somebody else's code too. But at the end of the day, just want to make a comment here. These are really just generalized additive models in some sense, if you're familiar with that terminology in statistics. They're really generalized additive mixed models. There's really a random component on there. That's kind of the state of the art, okay, for non-hierarchical models. And so if you can get a hierarchical framework into that, which we do through this stochastic transformations, then you kind of get the best of both worlds. So here's final comments, some challenges. Interpretation. I still don't quite know how to do that. I think that's what's come up a couple times already in this workshop. I think for statisticians, we have a problem with that. That we want to be able to understand what the components of our model mean. And so we're trying to do that in this context too. In the incorporation of scientific knowledge, and that's come up many times in this workshop, I think that there's more of a potential to do that in what I just presented than there might be in a traditional model. But until I show you that, I can't say that for sure. If you're a scientist and you're interested in doing inference, not just prediction, this isn't going to help, right? We've got to do something different. And that's where the traditional hierarchical models can play a role for this kind of complexity. Because you can do formal inference there, and you can understand each component of the model. But it makes sense, because that's probably the scientist is going to spend the time to do it. It doesn't have to be off the shelf. Something that hasn't come up to my knowledge is the notion of sampling. Statisticians spend a lot of time thinking about how their data were collected. And it makes a difference, right? I mean, I work with people at the Census Bureau, and there are billions of dollars spent on figuring out how to sample data, right? And if you ignore that information, right, or you assume it was sampled in a way that it wasn't, you do that at your own peril. And I haven't seen many people talk about that in the context of these deep models, but it's important, right? Where did your data come from, and how was it sampled, and how does that affect what's going on? The other thing that I haven't seen done much, but that doesn't mean it hasn't been done, is this notion of a multi-type output. The future of space-time modeling is in multivariate spatial-temporal modeling, or multi-process modeling. And when we do that in the environmental world, it's not all Gaussian, and it's not all percentages, and it's not all categorical or 0, 1, right? It's everything. If I'm doing precipitation over here, I have a different support than if I have temperature over here, and wind has a circular support, and then I might be interested in, you know, something that's has happened or hasn't happened. So if you do all that simultaneously, right, you have this multi-type output with all these complex dependencies. I mean, I don't think anybody does that well yet, right? There's some attempts like with copulus and things to do it, but that's an open problem, to my knowledge. I just, you know, but until we're not going to do any sort of real Earth system modeling until, from a stochastic point of view, until we can deal with that problem efficiently with complex dependencies. And then finally, what can you use this with? I think these kind of models that I'm presented would be wonderful emulators. Like if you have a computer model, and this has come up, right? This is this notion, kind of the Paul Allen stuff, right? If you want to build an emulator to emulate cloud resolving stuff, this would be a perfect model to do that with, right? Super low dimensional, super fast. You could use this to kind of go between models as well. It could also be used, and we're starting to do this in the context of design. By that I mean like targeted observations. Where should you take the next observation? Or what's also done less frequently, but it's going to be more important. Most of our data is redundant now, right, in big data problems. And the challenge is to sort of figure out which data you don't need. That helps not only with data storage, but it also helps with modeling. And so I think these kind of models can help with that too. So my last parting question is, you know, does uncertainty matter? And that's just rhetorical. This is the paper that I just talked about that Patrick has on the archive, and then some other references. I'm happy to send you that. It's a shameless plug, but it's shameless only because it's a new book we have coming out, because it's going to be free. If you want to buy it, you can, but don't. I mean, right. But I think you know, it's not easy if you've never done spatio-temporal modeling. The data structures are kind of crazy sometimes. The models aren't so useful. So we wrote this book. There are a bunch of, if you're familiar with the James et al. Sort of baby machine learning, statistical learning book, there's a bunch of R tutorials in the back of each chapter, and that's what this has too. Hands-on stuff, again, free to download. It's at the publisher, so it could be out at any point. So thank you so much for your attention.